the first of our two sets of homework that we had last night is up on the board. Page 305, number 7, 8, 9, and 11. Stephanie, questions with 305? Yep. Okay. That's a good question. Yeah, that's a good question. If you didn't hear that question, guys, Stephanie said, Lana, Stephanie said, when you're transferring your energy, converting energy from one form to another, right? In this case, elastic potential energy into kinetic energy. And they're saying we're transferring all of its energy, right? Stephanie said, wouldn't you lose a little bit when you do that? The answer is absolutely yes. Okay, we have to assume in this question, we have to take this question at its word. It says that all of it's transferred. But in the real world, that wouldn't happen. In the real world, you would lose a little bit. You guys learned in Science 10, second law of thermodynamics, right? Remember that? It said, anytime you do an energy conversion, you lose a little bit, right? Anytime you do, including when you're converting elastic potential to kinetic. So, Stephanie, we're going to assume here that it is all converted because that's what they tell me. But in the real world, that wouldn't happen. Good question. Anything else to look at here from page 305? 9? 7? Okay. Let's take a look at 7 and 9. Number 7 says you're working on the 5th floor of a building at a height of 18 meters above the sidewalk. Construction crane lifts a 350 kilogram mass from street level to the 12th floor of the building, 22 meters above you. Relative to your position, what's the gravitational potential energy? Street level when it's on the 12th floor, and what's the change in gravitational potential energy as it's raised? I don't know about you guys, but I think this is the numbers here and relative to this and the frames of reference are a little bit confusing here. I think it's easier to draw a picture here, just to keep things straight. So here's the ground level. Here's the 5th floor of the building, and that's 18.0 meters above. That's where you are. So let's draw you there. This is not a free body diagram, right? This is just a situational diagram, we sometimes call it. It shows what's going on in this situation, right? 70? We're lifting a 350 kilogram mass to the 12th floor. This is the 5th floor. This is the 12th floor. And the 12th floor is 22 meters above you. We want to find relative to your position, so everything is relative to you, the gravitational potential energy at this point, at street level. We want to find it at this point on the 12th floor, and we want to find the change in gravitational potential energy as it's raised. Hey, what would the change in gravitational potential energy be equal to here? Forget about the number. What term is the change in energy the same thing as? Yep. Work, yeah. So in other words, it would be, we find the answer to C, the change in potential energy as it goes from here to here. We're finding the amount of work done to raise this 350 kilogram mass from here to here. All right, so let's get the potential energy at the bottom here. We say it's m times g times h. The mass is 350 kilograms. G is 9.81. H is, what would we make h here? Remember, it's relative to you. So what's the height of that 350 kilogram mass on the ground relative to you? Derek? Good, negative 18. So we multiply these together, 350 times 9.81 times negative 18. Anybody have an answer there for that? Haley's question, why do we do negative 18 here? If we're finding it relative to you, and you're 18 meters above, then we'd say it has negative 18. In other words, to get to zero potential energy, right? Relative to you, you're at zero potential energy. That's what we're defining because that's where they tell me to define it. You have to absorb a certain amount of energy. You have to get a certain amount of potential energy to get it to that height. So we'd say it's negative. Honestly, if I was doing this question and it didn't say relative to you, I would never choose me as the frame of reference there. I would never do that. I would have chosen the ground as the frame of reference, right? I think it makes a lot more sense than choosing you. But I think they're doing this to illustrate that, okay, we can have different frames of reference, even if it doesn't make the most sense. What's the answer there, guys? 61,800 and thank you. Thank you, Jacob. We're going to round that to 3 digits, 6.18 times 10 to the 4 joules. But we're going to leave the unrounded number there as well because we may need that for question C. The potential energy on the 12th floor is going to be EP is equal to mgh as well. Mass is still 350, G is still 9.81, and the height is, this time what are we going to use, 22 or 40? Right? 22. We're looking for the height relative to U since we're looking for the potential energy relative to U. So it's 350 times 9.81 times 22. What do we get for that? What is it, Ryan? 75,537 joules. This one should have been negative, by the way, right? That one should have been negative. So we're going to round that to 7.55 times 10 to the 4 joules. Now, we want to find the difference. That's question C. All we're going to do is subtract the final minus initial. 75537 minus negative 61803. We're not just subtracting 61,000, we're subtracting negative 61,000. So when we subtract those, it ends up being the same thing as adding them, right? Which gives me something like, I don't know, 137,000, something like that. 1.37, positive 1.37 times 10 to the 4, 5. All right, how many people got that? Okay. All right, let's take a look at number 9 as well. This one says 2 cars, A and B, each have a mass of 1,200 kilograms. One of them is going at 12 meters per second. 180 degrees, by the way, is this way. The other is going at 24 meters per second at 180. They both increase their velocity by 10 meters per second. What's the gain in kinetic energy of each car? Delta EK. Can we do this? 1/2 m times delta V squared. We allowed to do that? Aiden, are we allowed to do that? No, we're not. If it was mgh and it was delta H, we could do that, right? But H wasn't squared, V is squared. So we're not allowed to do that. We've got to say delta EK is equal to the final kinetic energy minus the initial kinetic energy. And the final kinetic energy is 1/2 mvf squared, and the initial kinetic energy is 1/2 mvi squared. So let's do the first one. Let's say the 1,200 kilogram car. It's 1/2 of mass. The initial speed is 12 meters per second. I don't care what direction it is, by the way, because kinetic energy is a scalar. So if it's going to the left, doesn't matter. Going to the right, going 37 degrees west of north, doesn't matter. V is a scalar, so V is a positive number, any way you look at it. Sorry, that's the initial, isn't it? The initial kinetic energy is 1/2 of 1,200 times 12 meters per second. What's the final speed of this car, though? If it increases its velocity by 10 meters per second, what's the final speed, Lewis? 22. We can do that math now, right? 1/2 of 1,200 times 22 squared minus 1/2 of 1,200 times 12 squared. Whatever we get there, I'm not sure what it is, but it's a pretty straightforward calculation. We could do the exact same thing as the other for the other car. Okay, we got the first car. We could do the exact same thing for the second car. The difference here is that the second car would be, the initial velocity would be 24. The final velocity would be 34 because it increases its velocity by 10 meters per second as well. In question B, here's the good question right there. There's the understanding question. If both cars gain the same amount of speed, why do they gain different amounts of kinetic energy? And if you calculated those numbers, you'd find that they gain different amounts of kinetic energy. Okay. Can anybody explain that to me? If they gain the same speed, shouldn't the amount of kinetic energy they gain be the same? Good, because it's speed squared. If we could say delta V squared, then it would all be good, right? It would all be the same gain in kinetic energy. But because it's 1/2 mv squared, and EK and V are it's an exponential relationship, then doubling the speed or increasing the speed by 10 meters per second isn't going to have the same effect when the initial speed was different. If it was mv, It would. If it's mv squared, it would. Who asked me for that one, 9b? Who was it that asked me for 9b? Is it good? All right, the second bit of homework you guys had was page 294, questions 1 to 3 reassigned. Any issues with those questions? This is on that idea of work, right? Work that we defined as the change in energy, but we also said was equal to F times D. Well, we said it was F times D sometimes. We said it was F times D times cos theta sometimes. When was it FD and when was it FD cos theta? Well, if I pull a wagon at an angle of 30 degrees and it moves horizontally, then cos theta is the one that I use. If I pull the wagon horizontally and it moves horizontally, then FD is the one that I use. Bottom line is this. If I pull it one way and it moves the same way I pull it, then I just use the first equation. If I pull it one way, but it moves a slightly different way, if there's an angle in between the way that I pull it and the way that it actually moves, then we're going to use the second equation, F times D times cos theta. Are these questions all okay? Yeah. No, just because the question has an angle doesn't mean for sure you're going to use this one. We gave you that example yesterday when we were going through this. The angle of this hill is 30 degrees. You're pulling it up the hill here. And I think it was Stephanie, yesterday that said the angle that we would use there, we wouldn't use any angle. We'd go back to this equation. Why is that the case? Because I'm pulling it at 30 degrees, and it's moving at 30 degrees. It's not the angle that we want. It's the angle between the way that we pull it and the way that it moves. And in this case, that's 0, right? So we just drop that cosine theta and go to this equation. Most times, Ryan, when you see an angle, you're going to use it. But don't blindly just plug an angle in. Okay, look at it and say, okay, does that angle represent just anything, or does it represent the difference between the way that it moves and the way that I pull it? Okay? Which type of questions would I want to find to grab the gravitational force and the normal force? Like in one of these problems, you mean? Okay, remember when we did these ones? That was the gravitational force, this was the normal force, and then the force parallel, the force of the hill. We needed to get the gravitational force there. If we had friction involved here with the coefficient of friction, then friction would be equal to mu times the normal force. So we'd have to calculate the normal force there as well, right? Fg would be found by, m times g. The normal force would be found by the cosine function because we have adjacent and hypotenuse. So there's lots of situations where I need Fn and Fg. Fn typically comes into play when we've got friction involved, because we've got to say friction is equal to mu times Fn, but Fg comes into play tons. Neither of them would come into play in these work problems. We're good there? Okay. Wednesday, next Wednesday. I got one quick thing for you today, guys. I'm actually going to assign a little bit of a worksheet. I'll hand that out to you in just a moment here. I'll tell you what questions that is once I give you the worksheet out, okay? But while I'm on the train of thought here, what I'd like to do is introduce that last topic that we're going to do this week, cover one more small thing on Tuesday, or on Monday, sorry, and then we'll be good to go for Wednesday. Let's say that Haley and Brian live next door to each other. I don't know if they do or not, but do you actually live close to each other? Okay, relatively. So by relatively, you mean like basically in the same province? Okay. Okay. Well, let's pretend you both live. So I picked the wrong people because we're going to pretend that you both live in town. You both live right beside each other so that you both have identical driveways. Tomorrow it snows. It snows a lot. 34.7 centimeters of snow. You get up in the morning and you're thinking, yes, it's a snow day, there's no school. And then you realize, oh, it's Saturday, there's no school anyways. But Haley's parents and Brian's parents both make them to get up at 6:30 in the morning to shovel the driveways. So Haley starts shoveling at 6:30 in the morning. Their driveways are identical, right? They both live beside each other. They both have the exact same amount of snow. Haley starts shoveling at 6:30, but when she gets out to the driveway, she's like, yes, at least I'll have some company because Brian's shoveling his driveway as well. He has to start at exactly the same time. 37 minutes later, Haley finishes her driveway. 4 hours and 22 minutes later, Brian finishes his driveway. Who did more work? Who did more work, Haley or Brian? They both have the exact same amount of snow because their driveways are identical and they're right beside each other. But Haley took 37 minutes. Brian took 4 hours and whatever minutes. Who did more work? They both did the exact same amount of work. Neither of them did more work. If you're paying people by the job, by the amount of work that they did, then we're going to pay these two guys the exact same amount of money, right? Because they both did as much work as the other person. The work isn't any different. If we think about the average force that each of them applied on the shovel of snow, the average force. Now, each shovel is going to have a different amount of snow and whatever, but the average force that each of them applied and multiplied it by the average displacement of the snow as they shoveled it to the snow pile beside the driveway, it'd be the same value. So how do we quantify the difference then? If we want to hire somebody in the real world to shovel driveways, then we're not going to hire Brian. It takes him 4 times, 5 times as long as it takes Haley to shovel the driveway. How do we quantify that though? Because they both did the same amount of work. Well, we quantify that by using the term power. Power we define as the rate at which work is done. In other words, not how much work is done, but how quickly the work is done. Go ahead. Well, be careful. 4 hours versus 37 minutes is a time, right? But power it's certainly related to time because anything that's a rate is related to time. Remember, acceleration was the rate of change of velocity, time on the bottom. Velocity was the rate of change of position, time on the bottom. Anything that's a rate has time on the bottom. Power is a rate at which work is done. So power is going to be work over time. So what we're saying there is that, I mean, yeah, Stephanie, you could quantify just in terms of time, right? Not using power. You could just say, oh, 4 hours, 37 minutes. Okay, she was faster, so we're gonna hire her, right? But what does that mean? Like to the outsider who says 4 hours, 37 minutes. Yeah, but that doesn't tell me how quick a worker they are, because maybe Haley had a quarter of the snow that Brian had, right? If we just look at time, then it doesn't really provide us with a good comparison. Brian took a lot longer, but maybe he had a lot more work to do. If we want to compare how quickly they did the same amount of work, then we have to use power, which is the rate at which work is done, which is work over time. Basically, if they had to do 1,000 joules of work, don't write that number down right now, but let's say they both had to do 1,000 joules of work, but their times were different, okay, then Haley's number would be bigger, smaller time, bigger power in joules per second than Brian's would be. Does that make sense? The good news is this is usually a pretty straightforward concept, pretty easy concept, because in the end, if you can do work, right? Work, which is delta E, which is F times D, and sometimes FD cos theta. If you can do that, and you can because you didn't have too many questions when we went over the homework, then all you have to do for power is do that and then divide it by time. Simple as that. That make sense? Your homework over the weekend is going to be some questions on a worksheet, but in addition to that, you're going to do your own little experiment at home with power. You're going to measure the power output of your legs, how strong your legs are. Okay, are your legs more powerful than your legs? Are your legs more powerful than his legs? Okay, the power output of your legs. Here's how you're going to do it. You're going to run up the stairs. You're going to give her up the stairs. You're going to time how long it takes you to go up the stairs. Okay, I don't care which set of stairs it is, whether it's a set of stairs in the hallway here at school or whether it's a set of stairs at home, your basement stairs, I don't care. Okay, just do it safely. Don't run up ice-covered stairs or anything like that. Run up the stairs. Time how long it takes you to go up and measure the height of the stairs. Not the diagonal distance of the stairs, but rather the vertical height of the stairs. And you might have to figure out how to do that, right? For some staircases, it's easier to measure that vertical height. Some staircases, it's harder. But that's what you got to do. Measure the height, time how long it takes you, and get your mass in kilograms. So how are we going to do that? Well, we know that, how are we going to find that power? We know that work is equal to delta E, and it's equal to F times D times cosine theta. What kind of energy do you have at the bottom of the hill or at the bottom of the staircase? When you're standing there ready to go, what kind of energy do you have? You have chemical potential energy, yes. Yes, you do. In terms of mechanical energy, kinetic and gravitational potential, what do you got? 0, right? You're absolutely right, though. You do have chemical potential in your body. Mechanical energy, you have none. When you get to the top of the stairs, what kind of energy do you have then? When you get to the top. When you get to the top. You're not moving anymore. You've made it to the top. Okay, done. Whew. Wipe the sweat off your forehead. Gravitational potential energy, right? So if we say that work is equal to the change in energy, then we could say that power is equal to mgh final minus mgh initial, right? If I said find the work going from the bottom of the stairs to the top of the stairs, you'd subtract the final energy from the initial energy. Well, then let's do that. Plug it in for W and divide it by how long it takes you. That's going to give you a power output in joules per second. Energy is measured in joules, time is measured in seconds. But it also gives you the power output in a new unit that you've heard before, but not in physics, in watts. 1 joule per second is 1 watt. I want you to calculate the power output of your legs. And that's based on how quickly you run up the stairs. Now, just because you run more quickly up the stairs than somebody else doesn't mean you have a higher power output. I'm going to give you a situation where you ran quicker up the stairs than somebody else, but your power output was still lower. How's that possible? Yep. No, not the steepness, because it's all based on vertical height. Jacob, is your hand up? Okay, but if shares are, well, okay, fair enough, fair enough. Assuming equal height here. Okay? Even though I know you guys are all going to have different heights, okay, that's okay, because we're quantifying that, so that ends up being okay, and we end up accounting for that. Stephanie? Their mass, right? Generally goes like this. Generally, people that have a higher power output on their legs are generally people that aren't small. Okay? They tend to be not overweight people, but they tend to be people that are just bigger people. And the reason they tend to have a higher power output is because why are their legs stronger? They walk around, go ahead. They walk around every day carrying more weight. Right? If you lift, okay, if you're bench pressing 100 pounds, you're bench pressing 150, who's going to get stronger? Right? The person who's lifting more weight is going to get stronger. So generally, the people that are a little bit bigger have a higher power output. Okay? We'll see on Monday. Now, if you're interested, you don't have to do this calculation if you don't want, but if you're interested, you can. 1 horsepower is defined as 750 watts. So if you get a power output of 1,500 watts, then that means you're as strong, at least over a very short period of time, as 2 horses. Horses can maintain it for a little longer than you can, but for a short period of time, you're as strong as 2 horses. If you want to find out how many horsepower your legs have, then take that number that you got there and divide it by 750. Got that, guys?